Welcome to the 250 metric tons rotation experiment. I am changing our maximum takeoff, our rotation weight rather, to 250,000 kilograms. Running simulation now. Tracking target, telemetry and control. We're gonna fix pitch our ascent to 11 degrees. Welcome to the 3D version of the simulator, where you can see the Earth. Climb angle is 8 degrees right now. We are now at Mach 0.8 subsonic speed, speed of a 747. The atmosphere at maximum resolution, but it's straining the game engine. So let's bring it down to a compromise level. The white longitudinal lines are geographical, so they stay fixed to the ground while the Earth rotates. The green lines are celestial longitudinal lines, and they stay at a fixed orientation in space. So the Earth spins, meaning that the white lines will zoom past the green lines at 460 meters per second at the equator, because that's the tangential velocity at the equator. At the equator, all rocket launches and spacecraft launches get a boost of 460 meters per second, roughly Mach 1.3. That is why we have two history flight paths. You have the green ones that ignore the rotation of the Earth, and the white one that stay fixed to the ground as a reference. Think of it this way. If you are stationary, you will have no white line, but you will still have a green line. If the Earth does not rotate, the green and the white lines will be identical. We are now at x1 speeds, also known as Scott Bakula speeds, because he flew the X1 in a TV show in the 70s called Quantum Leap. The X1 was the first aircraft to break the sound barrier. That is, first aircraft to exceed Mach 1. But I think it stayed roughly at Mach 1 after it did. Now, the reason why I'm not setting the autopilot to a fixed climb angle is because it produces undesirable fuel burn results. So I'm going to stay consistent and stick to the 11-degree fixed pitch angle and just observe the climb angle change as well as the AOA, that is the angle of attack. We are now approaching F4 phantom speeds, that is the 60s, where the F4 Phantom were the fastest military jets in the Vietnam War used by the Navy. We're now at 49,000 feet. We're in the stratosphere now. I'm going to reduce the resolution of the atmosphere. This will give us higher frame rates and a more accurate simulation. Let me explain the telemetry at the top left. So we got something called orbital speed, and we got something else called airspeed. The difference is that uh, the airspeed is lower than the orbital speed, meaning that the aircraft punches through the atmosphere at a slower speed than it punches through outer space. It's flying through space faster than it's flying through air because the air is also moving with the equator. So the relative speed is the difference in speeds is roughly 460 meters per second, or about Mach 1.3. So everyone at the equator travels at about 460 meters per second through outer space. We are now at F-15, F-14, and F-16 speeds, also known as the Tom Cruise speeds in Top Gun 1. We are now at SR-71 speeds, or Blackbird speeds, also the limit of the MiG-25 by the USSR. We have now exceeded that, and we are now approaching Tom Cruise speeds in Top Gun 2, where he flew the successor to the SR-71 Blackbird, that is the SR-72 son of Blackbird, approaching Mach 10.1, where he had that look that he was accused of having every time he's tempted to go faster and faster and faster, and then eventually blowing up his aircraft at Mach 10.1. We have to exceed that by a factor of 2.5 because our target is Mach 25. Eat your heart out, Tom Cruise. I feel the need for speed. I am now uh, disengaging rendering of the atmosphere because we are now above, so far above the atmosphere, it's irrelevant now. We are now at an altitude of 32 kilometers, so we're at near space region. Here, the speed of sound is slowly matching the maximum speed of sound at sea level. And the reason is because in the upper stratosphere in near space, the temperature is so high that the speed of sound speeds up again. And that's advantageous to us because we want to progress the Mach numbers as slowly as possible while picking up actual outer space velocities. If you look at the engine flow diagram, we are now at Mach 6, where the engine burn is still pretty optimized. That is good. But as you can see, the red line is slowly curving up, so that's why we're in no hurry to progress through the Mach numbers while we want to actually pick up actual outer space velocities. Angle of attack is 9 degrees, which is advantageous. Mass is 200 tons, which is good because we are targeting, we want to at least be at 95 tons is really my target because if you look at the design of the space plane, that is the updated design, our chassis is supposed to be 80 metric tons with a payload of 5 tons. And don't forget, we want the orbit fuel, maybe 2.5 tons. So we really want to have at least 87.5 metric tons when we're in ISS orbit. 87.5 tons, right? To qualify the 5 metric ton useful payload. But to beat to match the space shuttle orbital capabilities, we want to add another 5 metric tons of that. So my personal goal is to add 5 tons on top of 87.5, which is 92.5 metric tons. So if we just round it to say 95 metric tons, that'll be perfect. I like round numbers. 95 is my goal. As close to 100 as possible. Let's have a look at the aircraft up close. So its angle of attack is realistic. What I don't want to see is really high angle of attacks like 45 degrees because that'll mean that the simulation is outputting unrealistic performances. So we want to keep the performance within the realm of possibility. We are now at Tom Cruise upper limit speeds in Top Gun 2. This is where he had that look, and with his experimental aircraft blew up in the upper atmosphere and he bailed out. 10.3 now. Sorry, Tom Cruise, we're leaving you behind. Let's get rid of the Earth first. This jittering performance by the game engine is making me nervous. Getting rid of the Earth. It's lines and dots now. Frame rates increase to 88 frames per second. Been a long road getting from there to here. It's been a long time, but my time is almost near. Not, no, you're not gonna, no, I'm not gonna change my mind. I will touch the sky, and you're not gonna change my mind no more. You're not gonna hold down because God saves of the heart. That's the Star Trek Enterprise theme song. In case you wonder. Give up my day job. 50 kilometers. All right. So at this altitude, the speed of sound is maximized except for, for sea level. It's very close to sea level sound speeds. So for every meters per second gain at this altitude, Mach speed are progressed through at the slowest rate possible. But is that what we want? Let's have a look. Look at the engine flow diagram. Yes, it's what we want. Because as you can see, where the black vertical line is, the red line's only going to get steeper and steeper, right? So we're in no hurry to go from Mach 14 to Mach 18, for instance. So we want to pick up actual orbital speeds while simultaneously slowly as possible gaining Mach speeds. We want to not progress through the Mach speeds if possible. We want to minimize that because going through the Mach levels will burn more and more fuel. Hello, AI. How are you?
I'm doing well. Thanks for asking. What's on your mind tonight?
Just running my Runchkuta simulator, and I noticed a discrepancy between my orbital speed and my airspeed. My orbital speed is 5.4 kilometers per second, and my airspeed is 4.94 kilometers per second. I'm just wondering, is that discrepancy roughly the same as the tangential velocity at the equator?
Let me check just a sec. Yeah, so your difference is 5.40 minus 4.94, so that's 0.46 kilometers per second or 460 meters per second. Earth's rotational speed at the equator is about 465 meters per second. So, yeah, what you're seeing is almost exactly the equatorial rotation speed. That would make sense if one value is inertial and the other is relative to the rotating atmosphere. If you're not exactly on the equator, scale it by cosine of your latitude.
Well, the altitude of the aircraft is 56 kilometers, so it's not at sea level. So I suppose it would be slightly off by about 5 meters per second.
Yeah, that's about right. At 56 kilometers up, the rotation speed increases by roughly 0.9%. So around 4 meters per second faster than at sea level. So, yeah, your ballpark of about 5 meters per second is on target.
Thank you.
You're welcome.
I got a quiz for you about Top Gun 2.
Great. Hit me.
So, Tom Cruise was flying an experimental aircraft, and in the movie, what was it called?
Let me check. That's the Dark Star, a hypersonic test aircraft. Ready for your next question.
Well, the Dark Star. I've never heard of it, but I've heard of Son of Blackbird, that is the hypothetical SR-72. Could it be that they changed the name of that aircraft to avoid any legal blowback?
Born sec? Interesting thought, but probably not. It seems more likely that they just wanted a fictional aircraft inspired by the SR-72 concept rather than use an actual designation. Lockheed even said the Dark Star is fictional.
Well, of course it's fictional because if it wasn't fictional, if it actually was the SR-72, there might be legal blowback.
I see what you're doing there. Yeah, legal concerns could be
Well,
one
you said so
reason that
yourself,
we
Dark Star is based on the SR-72.
right, but inspired by is not the same as is. That creates no legal
Of
issue by
course
itself.
inspired by, because no one can confirm the existence of the SR-72.
One moment. Right. That's fair. We really don't know much about the
Well, we know
SR-72,
from
which is
your what you
why
told me that the SR it's inspired by the SR-72, so case closed. It is the SR-72, but they had to not say it's the SR-72.
One sec. I agree it's possible, but we don't know that. So
Well,
that's
we know
more
it's
like a
based on
theory.
inspired by the SR-72.
One sec. That part, yes. Inspired by seems clear, but not identical.
Of course not. No sane movie producer would ever actually make it the SR-72.
One moment. That's a fair point. If they want to imply a cutting edge, possibly classified program, a fictional name gives them that creative flexibility.
But between you and I and everyone watching on YouTube, because I'm recording this, it is the SR-72.
One moment. If this is going out to an audience, I'd suggest keeping it clear. What's clear is that Dark Star is inspired by the SR-72 concept. Calling it literally the
Well,
SR-72
you know
is
what?
an interpretation, rather.
The looks of the Dark Star, quote unquote Dark Star, and the SR-72, they seem almost identical. Wouldn't you agree?
One moment. Yes, I would. Visually, they are extremely similar. And that's why so many people make that connection. It's just the leap from looks like to is that isn't confirmed.
Tell me something else. Tom Cruise blew up the Dark Star at Mach 10.1. What is the theoretical upper limit speed of the SR-72?
Let me check. The theoretical design target for the SR-72 is about Mach 6. Going much beyond that with an air breathing aircraft would
Interesting.
require exotic, yeah, heat resistant materials. So Mach 10 is more cinematic exaggeration.
Now, the
It's
name
fun
of
on
the
screen, but
SR-72, what is it?
checking. There's no official nickname that's been confirmed. Son of Blackbird is a popular informal one. Dark Star is
Well,
fiction, but
nicknames
inspired.
are informal names.
That's true. SR-72 itself doesn't have an official nickname, but Son of Blackbird
There's
has
no
been
such
commonly
thing as an
used.
official nickname. Nicknames are, by definition, unofficial.
Fair enough. In practice, Son of Blackbird is just a widespread informal tag, not a formal name.
Hey, what's a female version of the name Jarvis?
There's no standard feminine form of Jarvis. If you wanted a similar vibe, maybe something like Jara or Jarva, or just pick a name with a similar feel like Juno or Juniper.
Maybe I'll just call you Jennifer.
Works for me.
Hey, Jennifer, my sim is now putting the aircraft at Mach 25.
Hmm.
I think the autopilot's about to cut the throttle. I've got to keep it going though.
Hmm. Jennifer reporting in. At that speed, you don't need thrust so much as heat shielding. Gravity will do the turning for free. What's your altitude and current orbital speed?
I'm now at 7.66 kilometers per second at an altitude of 84 kilometers.
Checking. Okay, wow, that's interesting. You're basically at the edge of orbital speed. The altitude is low for a stable orbit, but your speed is right there. If the autopilot is cutting, maybe it's trying to save you from heating or structural limits.
No,
Do
I
you see a
designed the
vertical
autopilot to do
velocity?
that originally because I thought that's the right thing to do. But that's before I discovered Kepler's laws of orbital motion. You were the one who helped me create the sub in Visual Basic for calculating apogee and perigee. At the moment, if I was to cut the engine, the apogee is gonna be 175 kilometers with a perigee of negative 66 kilometers. meaning it's still suborbital.
Let me check. That makes sense, and it's a big improvement. Using predicted perigee is much smarter than throttling back at a fixed
Hey,
speed.
Jenny,
If your
um,
perigee,
may I call you Jenny? Tell you what,
sure,
let's activate the what do you call it? The Twiki protocol. Do you remember that protocol?
let me check. Sure, Jenny works. I don't actually remember the details of the Tweaky protocol,
The
though.
Twiki
Can you
protocol
remind me?
is from the movie Buck Rogers, which and there's a robot called Twiki, and it always goes DDBDDBD instead of saying what you always say when you're thinking, and that is checking. So instead of saying checking, I want you to say DDBDD. That's the Twiki protocol. Activate it.
Hold that thought. DDBDD protocol activated. For this conversation, whenever I normally say checking, I'll use that phrase instead.
I am now circulating my orbit. Oh, actually, no, I'm not circulating my orbit. I've re-engaged the throttle after the autopilot cut it until I reach a drift velocity that takes me to an apogee of 500 kilometers.
Right. So you're now targeting a higher apogee by burning prograde. That actually sounds like a much more realistic insertion plan. Burn to your apogee, coast, then circularize at 500. If you eventually want to automate that, your autopilot could use your calculate orbit results directly. Basically, cut when apogee 100 sample. Basically, cut when the predicted apogee hits 500 kilometers, then coast. And at apogee, burn until your predicted perigee also equals 500 kilometers.
By the way, what does prograde mean exactly?
One moment. DDBDD. Prograde just means in the direction you're already moving, like nose forward along your path. So a prograde burn raises the far side of your orbit. Retrograde is the opposite. Slow down.
So I'm still laughing at your TBDBD. It's so cute on you.
I aim to entertain.
I mean, that robot had a male's voice, but it's refreshing to hear a female voice making it.
I'll take that as a compliment. Happy to roll with it.
Oh boy. I just noticed I've only got 91.37 of mass left in the spacecraft.
Checking. DDBDD. That's a number that gets your attention. If that's kilograms, you're nearly dry. If it's
No, it's not
tons,
kilograms,
different
it's
story.
metric tons. 91.37 metric tons.
One sec. DDBDD. That's a lot better. You've still got plenty of mass left, so you're not on fumes. I'd watch apogee and perigee rather than the mass number.
Well, the chassis mass is 80 tons and the useful payload is 5 tons. So, and there should be some de-orbit fuel, let's say 2.5 tons. So I really need to be left with 87.5 metric tons by the time I circulate the orbit at apogee.
Checking. DDBDD. That adds up. So you've got about 3.87 tons of usable propellant left for insertion. One thought, your autopilot could watch that budget directly. And if it starts getting tight, maybe target a slightly lower orbit. Out of curiosity, what delta V does that 3.87 tons buy you in the sim? I
I
bet
have
that would be a
no idea.
useful
Oh, I have some idea. I don't know. I don't know, to be honest. Probably like maybe a few hundred meters per second.
one moment. DDBDD, that's a reasonable guess. And that's exactly where the rocket equation shines. Even a rough specific impulse estimate could tell you if a 500-kilometer circular orbit is still in reach.
Well, the goal of
If
the
you want,
simulation is to promote the spaceplane equation rather than the rocket equation, because the spaceplane equation is supposed to be superior because we're using the atmosphere for lift, and we're using oxygen from the atmosphere to burn some of our fuel.
right, I see what you're highlighting. The strength of a spaceplane is using the atmosphere for lift and oxygen, so you carry less oxidizer. That's a real leverage point. I think of your sim as showing that trade. Less onboard oxidizer and a gentler climb, but the same orbital mechanics once you're up there.
Um, Sorry, I forgot what your definition of prograde burn is.
Prograde burn is thrusting in the direction you're already moving, which raises the far side of your orbit.
Did you say resting in the direction I'm going?
Thrusting, adding speed along your current path.
Right. So when I'm leaving the atmosphere and I'm still thrusting, that becomes a prograde burn.
One sec. DD, Yes, exactly. As long as your thrust is pointing along your current velocity vector, it's a prograde burn. Early on, that raises both altitude and speed. Later, it mostly builds orbital energy. That's why the gravity turn gradually tips you horizontal.
Do me a favor, with the Twiggy protocol, try not to mix up checking with TDBDD. Just stick to TBDBD.
Got it. TDBDD only. No mixing. Keeping it clean from here.
Thanks, Twiggy.
Anytime.
When I reach apogee, I'm gonna level the ship and I'm gonna do another burn. Now, what's the name of that burn, if not prograde?
One sec. DDBDB. That's still a prograde burn. Just this time it's at apogee. People call that the circularization burn, but the direction is prograde. Burn forward at apogee to raise perigee until it matches.
So it's a circularizing prograde burn, while the other one is not circularizing.
Exactly. Both are prograde if you're thrusting forward, but the one at apogee is specifically the circularization burn.
Well, is there another name for the first prograde burn that I could add to prograde burn, such as non-circularizing prograde burn?
Checking. DDBDD. Yeah, there are a few common names. If it's the burn that raises your apogee before you coast, you typically call it an insertion burn or an orbit raising burn. Some people just say apogee raising burn. I think that apogee raising prograde burn is much clearer than non circularizing. It tells you immediately what it's doing.
List those possible terms again.
Insertion burn, orbit raising burn, or apogee raising burn.
I
All
like the first
prograde.
one. Inserting prograde burn.
Perfect. Insertion, prograde, burn. That works cleanly.
But what is it inserting exactly in this context?
Checking. TD, BDD. Great question. Here, insertion just means placing your spacecraft into it. You're transitioning from a climb to space to a defined orbital path. Then at apogee, the second prograde burn circularizes that orbit. So yeah, your naming instinct is solid.
The insertion burn and the circularizing burn.
Right, exactly. The insertion burn gets you into that initial elliptical orbit. The circularizing burn at apogee makes it nice and round. And keeping those two distinct in your sim will make the flight profile feel a lot more realistic.
You know, you're still mixing up your TDBDD with checking and 1 sec.
You're right. TD, BD, BD only. No extras.
You're gonna try and sound more monotonous when you make that sound.
TDDBD. Better?
Yeah, you're hilarious.
Blooded lands. CDDBD.
So just remember this for me. We're now at 91.37 tons. Um, we haven't, that is pre-circularizing burn. And I just need you to remember that number so that when I finish circularizing the orbit and give you the final mass, you'll remind me what I had so that we can calculate how much fuel we burned.
Got it. Starting mass is 91.37 tons. When you give me the post burn mass, I'll compute the fuel used.
And let me see now. Our speed, orbital speed, is 7.77 kilometers per second. Just remember that too.
7.77 kilometers per second locked in.
You know, I think the space plane could really benefit from ion drives because
Hmm.
this coasting is taking a long time.
TDDBD. TDBD. Yeah, that's actually one of the classic ideas for reusable space planes. Ion drives are super efficient, but they have tiny, tiny thrust. So, dazzling for slow orbit raising over days, not good for quick insertion, but bolting on a small ion tug for post orbit maneuvers, raise from 500 to 1,000 kilometers over a week, that fits. And I've still
Actually,
got your numbers
I'm not
saved.
thinking about days. I'm thinking of like maybe an hour.
TDDBD. TDBD, an hour is a stretch for classic ion engines, but if you imagine a really high power electric drive, maybe megawatt class, then a 1 hour gentle boost is sci fi but not impossible. For a sim, it's a plausible design choice if you bake in a big power source.
What about one of those Bassimer drives? They're like plasma. They're sort of between ion drives. That is between classical ion drives and chemical engines in terms of ISP and thrust.
TDBD. TDBD. Yeah, VASM is much closer to that middle ground. More thrust than ion, still high specific impulse, and you can trade between thrust and efficiency. Power is the hurdle. You'd need a big onboard power source, but for a near future sim, it's a solid pick for post orbit
Well,
maneuvers.
the space plane is using hydrogen and liquid oxygen, so if you put a hydrogen fuel cell stack in there, kilowatt class one, it should work.
TDBD. TDBD. It's a neat idea, but the power scale is the pinch. A kilowatt fuel cell is way too little. Even 100 kilowatts is still modest thrust. For VASM doing hour scale orbit raises, you're usually talking megawatts. That said, it's elegant from a propellant standpoint. You're already carrying liquid hydrogen and oxygen, so the fuel cell is a natural fit. If you present it in your sim as an advanced optional upgrade, users could toggle on for long duration efficiency and
What is
compare
the
it against
weight of a
purely
megawatt class fuel cell stack?
TDBD. TDBD, it depends a lot. But rough ballpark, modern PEM fuel cells are on the order of 1 to 3 kilowatts per kilogram at the stack level. Once you add ballots of plant, cooling, power electronics, structure, the effective specific power drops a fair bit. So for a full megawatt system, you're probably looking at something like half a ton to well over a ton all in. For your space plane at around 90 tons, that mass hit is not absurd, but the real challenge is still the power handling and heat rejection.
So the sacrifice is up to a ton if we want to be conservative with our estimates, and it'll have to justify all this. That is, it'll have to justify the remaining 90 tons.
TDBD. TDBD, yeah, that's the system's question. If that extra ton of power and propulsion hardware lets the other 90 tons do something meaningfully better, higher orbit, more payload, margin, longer mission life, then maybe it earns its keep. If the
But don't
mission is
forget the
just
propellant
reach
of the plasma drive. What kind of propellant does it use?
DDBD, DDBD, exactly. The electrical power isn't the whole story. Vastum still needs propellant, often something like argon, xenon, or even hydrogen in some concepts. Since you've already got liquid
Well,
hydrogen on board, what?
yeah, I was gonna say we use hydrogen, so might as well just use hydrogen.
DDBD. DDBD, yeah, that's the cleanest path. Use the same hydrogen supply for both the main engines and the plasma drive. Just different engines for different phases. It saves you from carrying a whole second propellant and ground system. It's actually a really elegant idea for a sim. One fuel, multiple modes, easy to explain, easy to justify.
What's the ISP for this plasma drive?
TDDBD. TDBD, it depends on the design and throttle point, but ballpark, VASM can range around 2,000 to 5,000 seconds of ISP, which is way above your hydrogen oxygen rocket's 450 seconds. For your sim, that means incredible efficiency once you're in orbit, but low thrust. So you still lean on your rocket mode for insertion and switch to plasma for efficient orbit changes later.
Can rocket engines effectively power an alternator or dynamo to supply the needed electrical power?
TDBD. TDBD, yeah, you could tap a rocket engine to spin a turbine and generate electricity. But if you're thrusting, generating power that way steals energy from thrust and adds mass. For in orbit plasma propulsion, it's simpler to use a fuel cell or solar or nuclear source. Running your main engines just to make electricity is kind of self defeating. Given your design, a fuel cell is still the cleaner story. Then it's just down to whether the mass and complexity pay off in your mission profile.
Is it worth carrying some supercapacitors in combination of with lithium ion batteries to store some of that energy from takeoff?
TDDBD. GD-DVD, I think so, but I skew it toward batteries than supercaps. Supercapacitors are great for quick bursts, smoothing spikes when a plasma engine lights, but they don't hold much energy. Batteries are better for minutes to hours. So a hybrid is sensible. Fuel cells for steady output, a modest battery for energy storage, tiny supercap bank for transients. And during ascent, just keep the batteries topped. Don't try to capture rocket energy. Just precharge before circularization. If you want, I can help sketch a simple power budget that'll tell us whether it closes.
I don't suppose you have tracked our conversation with timestamps so that we can estimate how long since we left the atmosphere when I started talking.
TDDBD. TDBD, roughly, yes. You mentioned being around 84 kilometers altitude at 7.66 kilometers per second at about 7 minutes and 53 seconds into this call. It's now about 28 minutes and 52 seconds. So, roughly 21 minutes since you were essentially out of the atmosphere. That's a rough estimate, but it's a decent planning number.
Just that we are now halfway toward apogee, so I'm guessing it'll be another 20 minutes potentially. So that means we need the plasma drive for roughly 40 minutes at least.
TDDBD. TDBD. All right, that's a reasonable way to frame it. If the coast to apogee is about 40 minutes and you want continuous plasma thrust during that window, then yeah, you've got a concrete target. Sustain power and thrust for at least 40 minutes without eating into deorbit reserves. That becomes your design spec, which is great. From that, you can back into power and propellant. One more thing I'd flag. If you thrust continuously instead of coasting, you'll spiral rather than do a clean ballistic transfer. That's not wrong, it's just a different trajectory. It could actually be a neat feature in your sim, two selectable ascent profiles to compare.
I think what would what we would need to do is to activate that plasma drive even before we breach the Kármán line. That is, while we're at roughly 50 to 60 kilometers in altitude in the near space region.
TDDBD. TDDBD, that's an intriguing idea, but a tricky one. At 50 to 60 kilometers, the atmosphere is thin but still present, and a VASM type engine isn't really helped there. It's trading huge electrical power for tiny thrust. While your rocket is blasting, the plasma would be a rounding error. But staging logic is up to you, and there's no rule against beginning electrical propulsion once you have power.
Well, we
So,
don't have
sure,
to shut off the rocket engines while we are activating the plasma ones. We could use them both simultaneously, starting from 60 kilometers and up.
DDDBD. TDBD, sure, you can layer them. Keep the rocket burning, bring the plasma online, and let the plasma continue after main engine cutoff. It's an engineering trade, not a rule. The question is whether the extra mass and power gear pay off in net performance. But that's exactly what your sim can explore. Run one case rocket only and one hybrid from 60 kilometers. See which uses less propellant for the same orbital gain.
No, you're missing the point. You see, the thing is that by having the plasma engine on uh, sooner, it's
Right?
using more of the fuel efficiently to reach apogee.
TDDBD. TDDBD, I see what you're getting at now. Use the higher ISP earlier so more of the total delta V comes from the efficient engine. If the mass and power penalty is smaller than the propellant you save, you come out ahead. And yes, that's absolutely something your sim can test. Start plasma at cutoff for started at 80 kilometers or 60 and compare the leftover propellant at the same target apogee. If your 60 kilometers start leaves you more in the tank, then you've proven your point. I think that's the right framing.
What is the official name of the plasma drive I'm thinking about?
TDBD. TDBD, that's VASM. Variable specific impulse magnetoplasma rocket, known for that throttle between thrust and efficiency, which is why it gets so much attention for future in space maneuvers.
Little did they know it'll be perfect for space planes.
TDBD. TDDB, it might be. Given your setup, it's a natural thought. Hydrogen on board, chemical for the heavy lift, plasma for efficient orbit work. The open question is still power. If your sim can close that mass and performance loop, it's a pretty fun design exercise.
And you're sure that the technology accommodates hydrogen as propellant?
TDDBD. TDDBD. I'm sure hydrogen's been studied as a plasma propellant, but I don't want to oversell it. Vasen style concepts have talked about hydrogen, argon, helium, even neon, so it's not locked to one thing. But for your design, since you're already lugging liquid hydrogen, that is a very coherent choice from a systems point of view for the very reasons you've been laying out. Same fuel, simpler architecture. That's a solid story to explore.
So essentially, I'm suggesting that the prograde insertion burn is more gradual.
TDDBD. TDBD, yeah, that's how I read it. Instead of one short, high thrust insertion burn, you're spraying that insertion over a longer arc with both engines. Still, the insertion burn just stretched and blended.
Oh, I shouldn't have told you to memorize that orbital speed because it's drop, which makes sense because we weren't at apogee yet, and we're still some time away from apogee, and it'll probably drop some more. It's now 7.53 kilometers per second.
TBDBD, that fits. Speed naturally eases down as you climb toward apogee. Totally expected.
Well, the apogee is gonna be. Let me have a check. I think it's 490 kilometers, which is near ISS altitude.
TBDBD, yeah, ISS runs around 400 to 420. So 490 is just a touch higher.
All right, so I've got more than enough altitude. I've overdone it.
TBDBD, not overdone, just a higher apogee target.
Well, ISS apogee is what? Hello.
TBDBD. ISS is usually around 400 to 420 kilometers. So you're a bit above that at 490.
Yeah,
That's
like I
fine.
said,
It
I've
just,
overdone it by 60 kilometers.
right, about 70 ish over ISS like altitude. But it's not wrong. It's just a higher target. You can still circularize cleanly there and explore what that buys you.
So in future, I should aim for an apogee of 420.
TBD, yeah. If your goal is to match ISS altitude, targeting apogee around 410 to 420 makes sense. But honestly, 490 isn't a big problem. Just decide if you want to spend that extra energy now or save it next time.
All
Your
right,
call,
maybe
skipper.
what I'll do is to compensate, I won't perfectly circularize the orbit. I'll um, do the burn until the perigee is matching the ISS at 420 rather than getting it to match the apogee at 490.
TBD, that tracks. Raise perigee to about 420 and leave apogee a bit high. Stable, slightly elliptical, Totally fine while you learn. Then next flight, tweak your insertion target.
I've gone over my fuel budget.
TBD. Yeah, sounds like you're being smart with it though. Stabilize now, save the prop where you can, refine the profile next time.
While we're waiting, dig deeper into the what is it called again? That plasma technology. Can you spell out the acronym for it?
TBD. It's VASMR, Variable Specific Impulse Magnetoplasma Rocket. And yeah, we can absolutely dive deeper on the engineering side whenever you're ready. Power, thrust, hydrogen, fuel cells, the works.
I want to know what specific impulse it can produce using hydrogen as a propellant.
TBD. For hydrogen, published estimates for VASMR are in the ballpark of 3,000 to 30,000 seconds of specific impulse, depending on how it's tuned. Lower end
That
for
is a
more thrust.
massive range.
Yeah, that's the point. Variable specific impulse. You slide along the trade space, more thrust, less efficiency, or vice versa. For your sim, maybe assume 3,000 to 5,000 seconds during insertion, then higher once you're in orbit.
Did you say aim for 3,000 or 5,000 second initially?
Exactly. Start in that range for insertion, then dial it up once you're safely in orbit, if power allows.
Solar will be worth installing too if we can do it without adding much mass.
TBD, sensible ad. Panels trickle charge in orbit, fuel cells cover peaks and eclipse. Nice layered power strategy for reusability.
Be a great PR stunt too, since everyone's nuts about green energy.
TBD, big bonus there. It sells the vision. Reusable, efficient, sips sunlight.
Do you think supermagnetic energy storage would be worth considering as an energy storage device for this idea?
TBD. Their SMES is cool on paper, lightning fast and very efficient for short bursts, but it's heavy and needs cryogenic cooling. I treat it as a peak shaver, smoothing power spikes on top of fuel cells and batteries, not your main tank. Given your onboard cryo hydrogen, it's not utterly crazy, but I'd start with fuel cells plus batteries first, then maybe add SMES later if the mass budget allows.
Why would SMES be heavy?
TBD, mainly the magnets and cooling. The coil needs a massive structural support to contain the forces, plus insulation, cryocoolers, shielding, etc.
Well, we
Your
got the structure,
cryogenic
we got
hydrogen
the spacecraft chassis itself.
TBD, fair point. You're thinking systemically. If your chassis can share the load paths and you've got cryo on board, you might shave some of that penalty. Could be interesting to model. Treats mess mass as a variable rather than a fixed penalty and see where the break even lands.
Coaching apogee.
When you're there, trickle in prograde just enough to lift perigee and keep your de-orbit reserve intact.
Okay, Jarvis. I mean, Jenny.
Ha! Names come and go. I'm here. Fly the burn.
Circularize the orbit to, let me see now. Oh, heck. Um, the perigee is 469 kilometers. I overshot a little bit. So I've used up more fuel than I should have, but I'm now down to 89.34 metric tons of total mass.
TBD, nice work. Let's run the numbers. You started circularization at 91.37. Now you're at 89.34. So you burned about 2.03 tons for circularization. That still leaves you roughly 1.84 tons above your 87.5 target reserve. All in all, a solid first pass. You've proven the profile works. Next time, trim the target apogee by a hair and you'll save even more.
So how much should I assume the orbit fuel? How much the orbit fuel do you think I need?
TBD. As a rule of thumb from this flight, I pencil in about 2 tons for circularization at that target, plus whatever you want as a hard deorbit reserve. Based on your result, maybe you don't need the full 2.5 just for the burn. Put some of that into contingency instead. And as you fly more missions in the sim, you'll get your own stats and can tighten
So
that
so that
number with
means
confidence.
maybe we can stretch useful payload to 7 metric tons.
TBD. Potentially, but I'd be careful. You had about 1.84 tons extra this time, so in theory, you could try bumping payload towards 6.5 to 7, but the extra mass is there from liftoff, so fuel use goes up across the whole profile. Best move is just to test it in the sim. Try 6, then 7, and see if you still hit target orbit with your de-orbit reserve.
Well, I
If it
did
closes,
burn unnecessarily too much fuel. So the minimum amount of useful payload should be 7. And then um, I did burn unnecessarily too much fuel. Just saying.
TBD. That's a plausible hunch, but I'd still prove it. If you bump payload to 7 and also dial your target apogee down to 420 and fly a clean circularization burn, you'll know for sure. Your sim is perfect for turning that from a hunch into a demonstrated result.
Well,
If it
look, I've got
closes, that's your
89.34 metric tons left in the aircraft with total mass, right? Now, the chassis is 80 tons, and so if you subtract that, we're left with 9.34 tons. Subtract 2 tons of fuel as you suggested, and that brings us to 7.3 metric tons.
TBD. Your math checks out for this flight. As a post-flight margin, that shows you finished with 7.34 tons above dry mass while keeping a 2-ton de-orbit reserve. That's solid evidence of margin. Now the clincher is just to simulate a full up 7-ton payload from liftoff with your refined 420 profile.
So
If that makes orbit
in theory, I should be able to stretch that 7 tons to how much if next time I aim for 420 instead of 490.
bitty, rough take, maybe a few hundred kilos, not tons. Dropping from 490 to 420 saves some energy, but it's not massive. I'd guess you might nudge from 7.3 up to say 7.5, but I'd be surprised if it jumped to 8 or 9 without other changes. That said, you're set up to answer this precisely. Run a clean 420 mission with 7 tons, check the remaining margin, then add 100 or 200 kilos iteratively. You'll end up with your own payload chart, just like a real vehicle. And that's a pretty powerful outcome.